And I'm going to begin my time this evening by asking you a question. And it's a bit of a controversial question. In fact, this question I find actually polarizes people. And if you answer the question in the wrong way, you could actually be branded a heretic, right? Because it's, for some people, the way you answer this question is a test of orthodoxy. So here's the question: Star Wars or Star Trek? Now, don't answer, because I don't want a fight breaking out in here, and I'm not going to tell you what I think about that. But I know what your answer most likely will be if you can tell me what this is. A Horta, right. So this is actually from a Star Trek episode. The episode was entitled Devil in the Dark, and it was written by Gene L. Kuhn, and it appeared in the first season of Star Trek, the original series. And this creature is a silicon-based life form that was terrorizing the miners on the planet Janus 4, which now I'm learning doesn't exist. And the away team beams down, and Spock does a mind meld with the creature and discovers that it's just simply a mother trying to protect her young, right? So it's a very, endearing story. But just a little bit of science fiction trivia here. Most likely the inspiration for this particular episode comes from an Isaac Asimov story called The Talking Stone, where he develops this creature called a silicone, like a coney, like a rabbit, a silicone. So it's really, really kind of clever. And I'm not going to read the description, but if you read the description and you actually read the story, you can see parallels between the Star Trek episode and between Asimov's depiction of this silicone-based creature. And all this leads to really the question, is it actually possible for life to be based on silicon? And the reason why this question is actually not just simply a question of curiosity, but is really significant with respect to what we're talking about tonight, is that when you present a case that interstellar travel is simply not possible for physical beings to endure, that the idea of alien civilizations is highly unlikely, given all the different requirements needed for life to exist, as Hugh pointed out, as Brian made reference to. Oftentimes the rejoinder to that is that you're just simply assuming life as we know it here on Earth, carbon-based life that lives in effect in an aqueous setting, right? But what about life as it doesn't, as we don't know it? What about the possibility of some other alternate form of life that could actually maybe survive interstellar travel at very high velocities, or could actually arise in different locations in our universe, in our galaxy, in our universe? And so the most likely alternative life form that could reasonably exist would be a life form that was based on silicon, not carbon. And I'll explain why that is in a minute. Now, it's interesting to note that this question of silicon-based life goes all the way back into the late 1800s, when an astronomer from Germany suggested that life could be based on silicon. And recently I saw a paper published, in a review paper published in a journal called Life, where a team from MIT pointed out that everybody talks about the prospect of silicon-based life, but nobody has actually rolled up their sleeves and actually done work to determine whether that's actually even possible. And their point is that there's two responses. Either people just dismiss the possibility outright, or they blindly accept the possibility. And so what they do in this paper is actually review silicon chemistry and make an argument for whether or not, again, silicon-based life is actually possible based on, again, the chemistry of silicon. And one of the first things that we need to do as we think about this question is actually ask, what are the chemical requirements for life? If life is going to exist, what does it require? Well, it has to be built around an atom that has certain properties. That atom has to be able to produce compounds that give you a rich diversity of chemistry. because life is very complex. And to support that complexity at a biochemical level, you have to have chemical complexity. You have to have chemical richness, chemical diversity. And that diversity takes on two faces or two facets. One is that it has to be structural diversity, that these atoms have to be able to form compounds with a variety of different molecular shapes, and they have to be chemically stable. You also have to have functional diversity, that these atoms have to be able to form compounds that can carry out a wide range of different chemical processes to support the complexity for life. And as it turns out, you also have to have this balance between both structural and functional stability and reactivity. If you are too reactive or too unstable, life isn't possible. If you're too stable and not reactive enough, life isn't possible. So there has to be a type of fine-tuning. And carbon is a perfect atom to satisfy these requirements. A carbon can form compounds where each carbon atom forms 4 chemical bonds. Its valence in chemical parlance is 4. The valence of carbon is 4. And these can be 4 single bonds, a double bond and 2 single bonds, or a triple bond and a single bond. And each of these types of bonds has very different geometric shapes. 4 single bonds leads to a tetrahedral geometry. A double bond and 2 single bonds is called a planar trigonal structure. And then you also have a linear structure if it's a triple bond and a single bond. But the point is that these different geometries give you a variety of different molecular shapes, which is, again, necessary for life. A carbon also forms stable bonds with itself and with hydrogen. And this allows for carbon compounds to form long linear chains, branch chains. They can form rings. The rings can fuse to form fused rings. There's even a chemical bonding that's highly unusual but very important, called an aromatic bond that carbon can form, that's necessary, again, for life to exist. And then last but not least, carbon can form chemical bonds that are stable with what are called heteroatoms, like oxygen and nitrogen and sulfur, and the halides like chlorine and bromine, iodine, and fluorine. And this is all necessary in order to create the chemical functionality you need for life to be possible. So carbon is this ideal, perfect chemical element that has all the necessary properties for life to be possible. Now, what about life based on silicon? Is this actually possible? Well, at first glance, it's not an unreasonable proposal. I don't know if you can see here, but if you find carbon, so if you go to the first row, you have beryllium, boron, carbon, and right beneath carbon in the periodic table is silicon. And in chemistry, if you know anything about the periodic table, any chemical elements in the same column have very similar chemistry. So of all the elements on the periodic table, the one that gives us the best chance of forming life that's not like we know it would be silicon. That is the best chance that you have for an alternative form of life. And if you look at silicon, it has again, can form 4 chemical bonds like carbon. Silicon can form silicon-silicon and silicon-hydrogen bonds. And it also can form bonds with heteroatoms. So this seems like, wow, this actually very well may be a possibility for an alternate form of life. But as the MIT researchers write, silicon and carbon are false twins. Their similarities are superficial and insufficient to mitigate their crucial differences. Chemistry that is stable and normal for carbon is unstable and exotic for silicon, and similarly, chemistry that is unstable and impossible for carbon is stable and routine for silicon. Silicon's distinct chemical characteristics and reactivity make it challenging as a choice for life. Now, in the next couple of minutes, I'm going to run through very quickly some of the differences between carbon and silicon that are absolutely crucial. That actually undermine the possibility of silicon-based life. Now, for some of you who may have a background in chemistry, some of what I'm going to say is going to be going to make sense. For some of you who don't have a background in chemistry, what I'm going to say is probably not going to make a lot of sense. But what I want to do is show you that there's actually good chemical reasons why silicon cannot serve as an element for life, as a basis for living systems. And so even if you don't understand the details, recognize that there are details that support that case. First of all, even though silicon can form silicon-silicon bonds or silicon-hydrogen bonds, they are less stable comparatively than carbon-carbon or carbon-hydrogen bonds. Why? Because silicon has a much larger atomic radius than carbon does. And that actually causes the chemical bonds it forms to be longer and weaker, and it also affects bond angles, which limit the geometry of silicon-based compounds. Silicon has low-lying 3D orbitals. Okay, unless you had a chemistry class, that makes no sense at all. But this is actually really significant because carbon doesn't. And these 3D orbitals actually make it possible for silicon to form compounds where it will form 5 or 6 chemical bonds, which actually adds to the chemical diversity of silicon. But the bottom line is that those 3D orbitals make the silicon-silicon bonds highly reactive and chemically unstable. Also, silicon can't form double and triple bonds. Only carbon can, and that limits, again, the molecular geometries. When carbon reacts to form compounds, carbon-carbon bonds are the preferred bonding. Carbon-carbon bonds are what carbon naturally forms. When silicon forms compounds, it naturally forms silicon-oxygen bonds. And this is because silicon is highly reactive in the presence of oxygen. And the product of a silicon reaction with oxygen is silicon dioxide, sand, right? Now, this is really, really important because when carbon reacts with oxygen, it actually oxidizes the carbon molecule, which is a chemical process that liberates energy that the cell can actually use to power its operations. So it's analogous to throwing a log on the fire, right? Or lighting a log on fire. A log is made up of carbon-based compounds. And when you set it on fire, heat is being liberated, light is being liberated, energy is being liberated, right? And you're generating carbon dioxide and water as the end products. Okay, the cell is doing the same thing. It's taking organic compounds, carbon-based compounds, and it's basically combusting them, setting them on fire like you would set a log on fire, but it's doing it in a highly controlled manner such that the cell can extract energy and make use of it for its operations, but the end product is the same. It's carbon dioxide and water. Now, this is really, really significant because carbon dioxide is soluble in water and it's soluble in air, which means that when a cell breaks down organic materials and produces the waste products of CO2 and water, that CO2 can diffuse away from the cell into the atmosphere. And it's a natural waste removal system, right? If a life form is based on silicon, the breakdown product, the oxidation product, is silicon dioxide, which is a solid material. And so that would kill the cell before it even could function. There would be so much debris that it would accumulate inside the cell if life was based on silicon that, again, life wouldn't be possible. There's no way to remove that waste. By the way, the solubility of CO2 and air and water also makes photosynthesis possible. So life on Earth is predicated on these highly unusual chemical properties of carbon dioxide. And then last but not least, silicon is more electropositive than carbon, which means at the end of the day that the bonds it forms with heteroatoms are longer and chemically unstable. So the bottom line is that silicon superficially looks a lot like carbon, and it's easy to see why science fiction writers like Isaac Asimov would create these silicon-based life forms. But when you actually roll up your sleeves and really examine the chemistry of silicon, it's much, much different than the chemistry of carbon in a way that really makes silicon-based life impossible. And so the bottom line is that we really can't have life as we don't know it. It's got to be carbon-based life, and if it's carbon-based life, it has to be carbon-based life in a water environment. That's the only possibility for life to exist on Earth or anywhere in the universe. And so the claim that interstellar travel is not possible for physical beings is a valid claim, even because it is based on carbon-based life forms. The authors of the paper from MIT write this: a silicon-based life that uses silicon exclusively as a scaffold element is often portrayed in science fiction. An iconic example of a fictional silicon-based life form is Horta from the 25th episode, The Devil in the Dark, of the first season of the popular science fiction television series Star Trek, the original series, itself possibly based on the silicone in Asimov's short story, The Talking Stone. However, silicon-based life that uses silicon exclusively as a scaffold element is almost certainly impossible. So anyway, science fiction aside, silicon-based life simply isn't possible. And so anyway, I'm done, and I guess we can transition to the next part of the program. So.
Thanks.